What is the dimmest thing we can image? Welcome to Seti Astro. This video is going to come with a lot of math, so if you're not big into math or the equations, you can just let that wash over you as we talk about it. And in general, everything in this video is going to have a in general in front of it too. So the vast majority of the information that I acquired for making this video is from the education notes here on stellar magnitudes and photon fluxes by Bishop in the where it's from the Royal Astronomical Society of Canada and provided through NASA's astrophysics data system. And I retrieved it actually from the Harvard open source educational page. So I'll have a link to this in the description below, but we're essentially going to work through this paper and then develop some real world scenarios from it. So let's go ahead and get into some real theory behind our telescopes. So the paper begins with using Planck's formula for energy emitted by a black body per second per unit area of surface. And it's between two different wavelengths. And all our units here are going to be in the square brackets, watts per square meter. And the first step to do is divide through by the energy of a photon. And we also have to integrate over all wavelengths of light. That's going to give us the total number of photons emitted per second per square meter of the surface of our black body object. That can only be solved numerically. There's no analytic solution for that integral, which gives approximately the 2.4 as a coefficient times a temperature cubed. So that's going to indicate to us that the photon flux is proportional to the temperature cubed. Now the paper goes on to consider the luminosity of the star using the bolometric magnitude and how far away it is from the Earth in parsecs. There's a law that tells you how much surface area there has to be if it is an ideal black body, which stars are pretty close. And then you could substitute all that in to actually get the rate of photon emission per second of the entire star. Now we could actually plug in some numbers into this, how far away a parsec is, how far the light was traveling, and derive an actual equation for the photon flux incident upon the Earth per square meter per second. Okay, we'll walk through a quick example where we are going to use the temperature of the star being 10,000 Kelvin. And the reason for that is the graph of the fraction of photons emitted by the star within the visible wavelengths that our eye can see peaks at around 10,000 Kelvin. So we're going to use that as kind of a best case scenario. So we could plug in 10,000 Kelvin into the temperature. For this example, we're going to use a magnitude of 6. And that's going to get us our number of photons per square meter per second, and then down to the 27,300 photons per square centimeter per second. And finally, multiplying by that fraction from the graph tells us that there's about 7,000 photons per centimeter squared per second incident upon the Earth. Now, I want to pause here real quick and say just how crazy that is, right? This is a star, so magnitude 6 is pretty much the limit at what the human eye can even see at a dark site. But even with that, 7,000 photons per second per square centimeter over the entire Earth's surface from a star that's many, many light years away should tell you just the unfathomable amount of photons an actual star is, how bright an actual star is. And at the same time, right, photons convey causality. Right, that's how nature talks to itself. So there's 7,000 times a second per every square centimeter of the surface of the Earth where that star has an actual causal link to our planet. And it I don't know, science, right? Sorry, geeking out. So let's take an example of a C-star telescope now. So a C-star telescope has a diameter of 5 centimeters, so it has an area of just under 20 square centimeters. If we're going to need 1 photon per second, and I'll talk more about this stuff, but let's say your detector is going to need 1 photon per second. That means in that whole surface area, it needs to get 1 photon. So it's 0.05 photons per square centimeter per second. You got to divide through by that stellar fraction of the photons that are visible from the star. So that gives us just under 0.2 photons per square centimeter per second. Scaling it up to meters per second, that gives us just under 2,000 photons per square meter per second. And now what we can do is rearrange our previous equation and solve for magnitude. And doing so in there yields a magnitude of about 18.8, which is pretty freaking dim. But that's assuming every single photon hitting the aperture of the telescope is a detection. So let's go into a more realistic scenario of what actually happens here. So the atmosphere itself is going to attenuate about 82% of the photons at a normal observing angle versus observing directly at the zenith. I chose 35 degrees off the zenith to get that 82% photon reduction, but it's a good average about, where we'd ideally like to be recording on average throughout the entire night. So out of 100 photons, we're left with 82 after that. The triplet design of the C-Star S50 as well has about a 98.5% transmission through all 3 of those elements. The AR coating itself on the lenses also has its own transmission of about 98%. Now the C-Star is unique. It has 2 diagonals inside there, each of which is about 98% reflective. Then we also have the micro lenses themselves on the Bayer matrix for the sensor, and the transmission of the dyes and the Bayer matrix as well. I put that at 98%. And then finally we have the quantum efficiency of the sensor. That does vary across the wavelengths that we're looking at, but on average it's 80% efficient across the full visible range. So out of, let's say, 100 incoming photons detected at the end were only 59. As we're building up our realistic view here, the next thing we need to touch on is something called median stability. Oof. Well, if you saw the other video, this is where it went off the rails. If you've ever wanted to crawl in a hole and never be seen again, this was me right now. So we're going to diverge from talking down this rabbit hole, which is completely wrong. I don't even know why I was stuck in like 16-bit mindset here. Even in Seti Astro Suite, I made a custom weighted 32-bit average method for integration. And I guess never stuck my head out of the sand and asked, is this the correct thing to be talking about here? So I do apologize for that. So let's carry on with the video. So our subframes are 16-bit, and I guess the general question is, how many 16-bit images can we fit in a 32-bit stack before we start getting quantization of the 32-bit limit? So if we start with a single frame, then we got 4 frames, which is about the limit that any stacking software will even allow you to stack as the minimum. Then going up to 16 frames, this is the point where rejection algorithms start becoming more robust. On up to 256 frames, and I think most people would think 256 subframes is starting to be a pretty good stack of images at this point. But to actually fill out the full 32 bits, we need 65,536 subframes. So let's see what that looks like. Gonna go out on a limb and say most people don't take 65,000 sub exposures, but that will be the limit that we're gonna start talking about in our discussion here. So when we're gonna be looking for the absolute limit of the dimmest thing, we're going to be limited by read noise. And I have some popular sensors up right now showing the read noise values. A lot of them have a high gain setting, so this one, depending on where you're imaging, but you're probably going to be imaging here at the 1.1. This particular sensor has a read noise of like 1.25 or a little more. This one is closer to 2. So in the rest of the discussion, I'm going to be utilizing 1.25 as a read noise average for a realistic modern sensor. So we have our read noise of 1.25 electrons. Stacking reduces the noise by the root of the number of frames we have. We have a ton of them. An SNR of 1 would be the 0.005 electrons. And an SNR of 3 would be 0.015 electrons per frame. And that's if you are using all 65,535. So if you had a stack of 65,000 sub-exposures, you could get away with 1 electron detected every 68 frames for an SNR of 3, which is the astrophysics standard for a detection. And this is showing some various stack sizes, less than 65,000 subframes, and how many frames per electron detected you would need, depending on those stack sizes, again with a read noise of 1.25 electrons. And now here's just graphically, SNR of 1, that's the signal exactly matches the read noise, and then SNR of 3, again, is actually what we need to utilize. Now this graph is a little misleading. I mean, who's getting 10,000 sub-exposures? So let's switch to a log scale on the x-axis. Now this really shows that, if you got 100 frames or so, like we showed in the graph, you need 3 frames per every detection. And less than that, it's even going to be more frequent. So the fewer frames you have, the more you're going to actually need a detection per frame. And then again, at the end of this graph is the hard limit of 65,536 sub-exposures if you take that many. These are assuming all those photons are concentrated and fall on a single pixel. But that's not how this works. The shape of the flux that hits your sensor is the shape of an Airy disk, right? Because of the wave nature of light, you're going to have a bright central peak, and then it ripples out. Now you can calculate the actual Airy disk, its radius, based on the aperture of whatever telescope you have. So again, we're just going to use the C-star as 50, calculate how many radians that's going to be, and convert that into arc seconds. We know how big that will be on the sensor, and we know how big each pixel is on the sensor. So we could figure out approximately how many pixels the Airy disk is going to end up covering. And it's going to be any fraction of roughly these 9 pixels in the center there. And I'm just going to use 6 for the calculation. Another quick thing to mention in passing here is after we finally get our final calculation done, whatever that may be, we have to account for the actual atmospheric extinction from space all the way down to the ground at zenith. And that's going to account for 0.28 magnitude. So you'll see that at the very end where we subtract that final little bit off. Let's put it all together here now. We're going to start with our rearranged magnitude equation, where we're going to calculate our incident flux. Our incident flux is going to be factors of our sub-exposure time, how many subframes we have, the aperture, and the visual fraction, and then the conversion from square centimeters to square meters. We could then plug all that in for our C-star example here and get a magnitude of 27. We could also recompute this for various other stack sizes that may be a little bit more realistic. Now, 65,000 30-second exposures is 550 hours. I don't think anybody's doing that. But maybe you got 1,000 or 128 exposures, and that'll be your limiting magnitudes there for an SNR of 3. But that's assuming every photon that hit the aperture actually was a detection. So now we got to factor in the transmission of everything in our optical train. Again, then transmission factor was about 60%, which gives a final magnitude of 26.6. And that last piece of 0.28 of an extinguishing factor leads 26.3 for the 65,000 frame stack. And again, now a chart showing some more realistic stack sizes there of 24 and 22.9 as the limiting magnitudes. And we can't forget our good friend, the Airy disk, where we're going to actually have to take and multiply that incident flux again by 6. Here's an example of where that comes into play. And now a full chart, everything included, transmission, atmospheric extinction, an Airy disk size. If you take it to the limit, the 32-bit limit with 65,536 exposures, letting you have the most, 1 out of every 68 frames should have an electron detected, is going to leave you about a magnitude 24.3. If you have 1,000 sub-exposures, your limiting magnitude is going to be about 22.1. And then for more realistic 128 36 exposures is limiting magnitude of 21. So now you may be wondering, how does all this fit together if you maybe have like a stack of 300 10-second exposures or 10 300-second exposures? How does that affect ourselves in the read noise limited regime, or maybe if the signal is higher and we're in a photon limited regime? If you really want in-depth video on this, please check out Deep Sky Details videos on noise. He does excellent production work on that, goes into a ton of detail. This is just going to be a quick touch on it for the purposes of our what's the dimmest thing you can image here video. So we're still going to be utilizing our 1.25 electrons as our read noise, and we're going to need to talk about the incident photon rate in electrons per second as well. Now, a more complete description of whether you're in the read noise regime or the photon regime is using a mixed SNR equation, and we're going to have our two stacking strategies, 300 by 10 second or 10 by 300 second. Now what we're going to want to do is compare these two different equations and see how they stack up against each other to see which one's better, or are they exactly the same, or what here. So we're going to start by taking the ratio of those two different equations. And then we're going to look at the limiting behavior. Now the limiting behavior, when your incident flux is much, much less than your read noise squared, so we're in the read noise limited regime, the ratio between the two is going to boil down to, in this case, the square root of 30, which is going to be the square root of the long exposure divided by the short exposure. So in this case, about 5.5. So for the very, very dimmest stuff in the image that's read noise limited, your longer exposures are going to be much better and detect fainter signals, in this case of our example 10 by 300 or 300 by 10, of 5.5 times dimmer objects, even though the stack length is the same exact length of exposure time. In the photon noise limited case, where you have a lot of SNR, that limiting behavior of the ratio is essentially 1. So you get the same exact total exposure time, whether the stack's 10 by 300 or 300 by 10. So that's going to be things like the bright cores of galaxies, bright nebula, planetary nebula, things like that. It doesn't matter if you're doing a whole bunch of short exposures or a couple long exposures. If there's a lot of photons to be had, it's going to give you the same total exposure. It's only in that read noise limited case where the stack is going to matter to have the long exposures. And here's just some numerical examples to show you how that ratio changes, that limiting behavior from the read noise limited domain at the top down to the photon noise limited domain at the bottom. All right, so where does this leave us in our search for the dimmest object you can image here? So first off, if you really want to go all the way to the actual limit of 32 bits, you're going to need 65,000 sub-exposures. That will be your hard limit. And with a read noise of 1.25 electrons, which is pretty average of all our sensors right now, that's going to give you about 1 electron you need to detect every 68 frames. Much more realistically, you're probably somewhere in the 100 to 1,000 frames. So even in that case, you're going to need about an electron detected every 3 to 10 frames or so in your stack in order to register as an SNR of 3 above the read noise. Once you know all that, you can go ahead and plug everything into your incident flux equation here to calculate your magnitude. Don't forget that you also have to factor in your transmission of all the elements and the quantum efficiency of your sensor, as well as that final atmospheric extinguishing factor that comes into play. And finally, if you really want to get really in depth into all the noise discussion and the theory behind the noise and all these different regimes, do check out Deep Sky Detail's excellent videos on the subject. He's a fabulous creator, and I highly respect all the work he does as well. Please check out his videos on noise if you want further in-depth discussions. Please comment, like, and subscribe.